Hey fast learners, today we are going to go through the parallel axis theorem. The parallel axis theorem states that the moment of inertia of a rigid body about any axis is equal to the sum of its moment of inertia about a parallel axis through the center of mass and the product of the mass of the body and the square of the distance between the two parallel axes. Allow me to repeat on this. We are trying to say that in order for us to gauge the moment of inertia of any axis on a body, we need to know some criteria. We need to have the moment of inertia about the center of mass, and then we add the product of the mass of that body and the square of the distance between the two axes, whereby I of cm represents the moment of inertia about the center of mass of the body, I of s represents the moment of inertia about any point on a body, and m represents the mass of the body, and d represents the distance between the two parallel axes. So anyway, we have our body with this axis which is through the center of mass, and with another rotational axis through the center rotational axis, with another rotational axis which is passing through any point on the rigid body. The two axes have a distance d apart. They are distance d apart, and we have an element dm of distance r from the axis through the center of mass, and a distance rs from the rotational axis. So repeating this, that we have a body which has an axis going through the center of mass and another parallel axis which is the rotational axis about any point on the body. We have an element dm which has a perpendicular distance r from the axis that goes through the center of mass, and a perpendicular distance rs from the rotational axis. Let us start with a general equation. The moment of inertia about the center of mass is equal to the integral of r squared dm. This is a general equation that says that for us to get the moment of inertia about the center of mass, we shall have to integrate the square of the perpendicular distance with respect to dm, to the element dm. On calculating the moment of inertia about another axis, which is the rotational axis, we shall get this by integrating the square of the perpendicular distance rs, which is from the element dm. On our shape, we can see that rs, the perpendicular distance from the element dm, rs, is given by the distance between the two parallel axes d plus the perpendicular distance between the axis through the center of mass and the element dm, meaning that for us to get rs, we have to add d plus r, whereby d is the distance between the two axes and the perpendicular distance between the element dm and the axis to the center of mass. On squaring both sides, rs squared equals to d plus r, the whole thing squared. So when we replace back our rs squared back in our r of s, we have the integral of d squared plus 2dr plus r squared with respect to dm. On splitting the integral, when we go on and split the r integral, we generate the integral of d squared dm plus 2dr dm plus the integral of r squared dm. But before we move on, let's first find the center of mass of the original object. By definition, the center of mass along the x-axis r equals 1 over m integral of r dm. By definition, the center of mass along the x-axis is r equals to 1 over m integral of r dm. And because we are centered about the origin, 1 over m integral of r dm equals to 0, meaning that the integral of r dm equals to 0. Let's proceed to the proof. Recall we have the integral of d squared dm plus 2dr dm plus r2 dm. By rearranging and pulling out the constant out of the integral, we have our I of s being the integral of r squared dm plus 2d integral of r dm, since 2 and d is the distance, that constant distance between the two axes, plus d squared by pulling it out, integral of dm. I of s equals I of cm, which is the, by definition, the integral of r squared dm equals to ICM. That's why we now, on our next step, our I of s equals to ICM plus 2d integral of the integral of r dm. As we have proved, this whole expression will tend to 0, as noted earlier that the integral of r dm tends to 0 plus d squared integral of dm. So we end up having I of s equaling to the I of cm plus d squared times m, whereby we have m, since the integral dm equals to the sum of the little elements. That should give us the total mass m of the object. They should give us the total mass m of the object. Therefore, moment of inertia about any axis equals to the moment of inertia through the center of mass plus the mass of the body multiplied by the square of the distance between the two axes. Hence, this is the proof of the parallel axis theorem.